Okay, this video is on vapor pressure, and a couple other pieces of information, volatile liquids, and boiling point. So this kind of goes along with our intermolecular forces discussion, and some of this is a review that we should have seen in Chem 2. So I'm starting off by, well, I guess here, let me show you. We're on this piece of paper for your notes. So, okay, starting off by talking about vapor pressure, which happens in a closed container. So that's important. I drew a container and I, try to put a lid on it. Okay, so the idea of vapor pressure happens in a closed container. And what happens is molecules eventually gain enough kinetic energy to escape the liquid surface by the process of evaporation. So you can think of, here's your liquid, and then eventually enough, or some of those molecules are able to separate from each other, which is a discussion of breaking the intermolecular forces, and are able to evaporate. Okay, so if it's in a closed container, these molecules then start colliding either with each other or the walls of that container. And we know from our discussion in gases, anytime you have a collision, you create a pressure. And so those collisions create a pressure above the liquid. Okay, so obviously it's a pressure up here. And that pressure is referred to as a vapor pressure. Okay, so a pretty simple idea. The more molecules that have evaporated, the higher the vapor pressure, right? So the more collisions, the higher the vapor pressure. Sometimes we will end up talking about if you end up heating up a liquid, right? The higher the temperature. So we can write that, we'll add that. So the higher, or let's do arrows to make this easy. So the higher the temp is the higher the kinetic energy. Oops, I forgot my K. The kinetic energy of the particles, which means an increase in collisions, which means an increase in this idea of vapor pressure. Okay, so that's kind of a takeaway point. And the same could be said for the reverse of that. Lowering your temperature decreases your kinetic energy, it decreases your collisions, and it decreases your vapor pressure. So that's kind of a big takeaway. All right, so let me erase this. And I have somehow lost my black dry erase marker, so we're going to blue. Okay, so let's see. Vapor pressure at the molecular level. So we'll do VP at molecular level. Okay, so let's see. We constantly have we have particles evaporating. So going from liquid to gas, right? Getting caught above that liquid, creating a vapor pressure. That was just our discussion from a second ago. So as that happens, as evaporation happens, so does condensation, which is, of course, the opposite. So, and that's a gas going to a liquid. So I'll draw my little picture here again. All right, so remember this is a closed container. Okay, so if I have a closed container and I have particles in my liquid state, eventually they're going to gain enough kinetic energy and they're going to vaporize. So we have this process that's kind of happening, liquid going to gas, evaporation. Well, as that occurs, because it's like a closed container and those particles have nowhere to go, of course, they're creating a vapor pressure. But then some of those gas particles also condense. So some of these gas particles go back and turn into a liquid through the process of condensation. So eventually, and that's important because it's not immediately, the rate of evaporation equals the rate of condensation. Okay, which basically means the number of particles that are evaporating is equal to the number of particles that are condensing. And this is referred to as, I'm going to do an arrow, it's referred to as a dynamic equilibrium. Dynamic because there's movement. Okay, so there are still particles evaporating and still particles condensing, but it doesn't look like it. So that's kind of a point that is worth saying. It looks like nothing is happening. And that's only because there's no net change. Meaning, so if you had, for example, 5 particles evaporate at the same time that 5 particles condense, it would look like to you, the viewer of this, that nothing was occurring, when in all reality something is occurring, but it's that there's no overall change, and so it looks like nothing is happening. We're going to learn later that this is true in reactions, which is the whole chapter on equilibrium, and this is just kind of the intro to that. So that's a discussion of evaporation and condensation and dynamic equilibrium. Now, we made a big point about this happening in a closed container. This does not happen in an open container, so if you want to add that, you can. And it doesn't happen in an open container because those particles just escape, right? There's nowhere for them to go. I mean, there's everywhere for them to go. Sorry. In a closed container, there's nowhere for them to go. So in an open container, this doesn't happen. They just escape. Can you see? Is this too low? Oh, that's too low. I'll add it up top. Does not happen in open container. So actually in the past we've used a water bottle as an example with a lid on it. If you left your water bottle in your car like for forever, it would never fully be empty because while some of those particles are evaporating, some others are condensing, and it's just going to stay that way forever. And that's the idea of equilibrium. So, all right. Okay, what's next? Volatility, vapor pressure, and temp. And actually, we already talked about vapor pressure and temp, but that's okay. Okay, so, oops, sorry. I don't mean to turn my board for you. Let me get that back. It's easier for me to write. Okay. So, liquids that evaporate easily or readily, you might hear it said, are said to be volatile. Okay, it doesn't necessarily mean they're reactive. It just means that they evaporate much easier than other liquids. And I bet you can't guess what this is dependent upon. It's dependent upon intermolecular forces. So water, for example, H2O does not readily evaporate, although you might think that it does. It takes a lot of energy to get water to evaporate. And that's because if you step back just for a second and think about it, water has hydrogen bonds. And hydrogen bonds take so much energy to break. So something else like rubbing alcohol is a really good example. If you pour rubbing alcohol on your counter, it evaporates pretty quickly. And that's because the intermolecular forces in rubbing alcohol are much weaker than those in water. Okay, so this is completely dependent upon intermolecular forces. And then kind of a common sense point of this whole vapor pressure and temp, I had written that hot water evaporates much quicker than cold water. Now, again, that's a little bit interesting because they're both hydrogen bonding, of course, because they're both water. But this is the idea of something that's hot has more kinetic energy and thus more energy to break those intermolecular forces. So an increase in temp means an increase in kinetic energy. And that's what this is all about, okay? That increase in kinetic energy. So volatile just means evaporates easily or readily. It does not really mean reactive. So be careful about that in a definition. And then the very last topic on this paper is boiling point. So vapor pressure and boiling point. Okay, so the boiling point of a liquid is defined as the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. And so this was a topic that was discussed in Chem 2, and we discussed the fact that, so wait a minute, that means that the boiling point of something is dependent upon the atmospheric pressure. So when we talk about the temperature at which something boils, we have to kind of define that, since we now know that it can boil at a variety of temperatures. So we define something as the normal boiling point, which is the boiling point at 1 atmosphere of pressure, okay? And so the word normal means at 1 atm, and that's, of course, sea level. And so we talk about the normal boiling point of H2O being 100 degrees Celsius because water boils at 100 degrees Celsius if the atmospheric pressure is 1 atm. We have learned that if we change the atmospheric pressure by changing the altitude, then our boiling point changes. And we used to talk about that, going to Denver, right? I don't know if you can remember that. But that up on top of a mountain, the pressure decreases, which means your boiling point decreases. And so for water, for example, it's about 95 degrees Celsius in Denver that it boils at. So it boils slightly lower because your pressure is lower. If you were to go, down below sea level, for example, and I don't necessarily mean underwater, but I mean below sea level, your pressure would be increased, and that would mean your boiling point would be increased. So it would be higher than 100. So higher than 100. We used to talk about, a vacuum chamber per se, and being able to, could you make water boil at like room temperature? And yeah, absolutely. But you would have to take a lot of the pressure out using something like a vacuum chamber, but you could. So we know boiling point is dependent upon atmospheric pressure, and so we define the normal boiling point of something as 1 atm. And we also know, and maybe I should make a huge point of this, which I think is kind of the idea throughout this whole section, is that that marker doesn't work, is that boiling point depends on intermolecular forces. I bet you couldn't guess. So a higher boiling point means a stronger intermolecular force. And if that's not a takeaway, I don't know what is. And so we talk about water having, a pretty strong intermolecular forces. And because of that, water has a very high boiling point compared to other substances. So if we look at boiling point data, we can often make some assumptions, maybe not some assumptions, we can often infer some things about the intermolecular forces that exist within molecules. So takeaway point is that intermolecular forces are let me back up. Takeaway point, a lot of properties are dependent upon the intermolecular forces in a molecule, and that's why intermolecular forces are so important.